You didn't see that, right? Good. Just waiting to be live because it will also be streamed on YouTube. So we are live. Great, I guess so. All right. Technical check. It doesn't work. Very good. Let's just. Yeah. Okay. Welcome everybody. I'm very glad to see so many different people of so many different parts of my life right now here in Frankfurt, and it's a great pleasure to have you all here. Were you ever in a moment where you were thinking, hey, wait for a moment. How did I end up here? How did all of that happen? And this moment is actually not today, because today is just too much going on, but this moment was last week at the department. I was like, wait, it's the end of my PhD. When did I finish my master? When did I finish my bachelor? Wait, high school? Or what was the thing with the rocket back then? Wasn't that just yesterday? No worries, I won't tell you about my life story now, because you're actually here to hear about my PhD. To new frontiers. How can we make it to new frontiers in the sense of nanotechnology and space exploration? And I want to start with first, before I really go deep into that, I want to start with giving you a little bit of an overview of what happens today. So right now we're in the middle of the layman's talk, where I just explain a little bit in more easy terms I try to explain in more easy terms what I did for the last 4 years. After that, there will be the official defense, which takes exactly 1 hour. Then the committee retreats, the committee comes back, and then I may or may not get my certificate as a doctor. And after that, we celebrate, or we are all sad, depending on the outcome. We will have a reception here in the building. Actually, it starts already at 11:30 and goes to 2:30, which is great because it's more time for drinking and eating. It's actually here in this building, in the Franz von Hasel Saal, so you're all very welcome to join in there as well then. And in the evening at 8:30 p.m. we will have a big party at the Wacht. Also, all of you are very welcome to join in there and celebrate or be sad together with me together today. All right, my PhD work, To New Frontiers. I want to actually start with a bit of with a quote and with, oh, how does that work now? Very well prepared.
9 or 8.
So maybe some of you note or remember this very specific day for space exploration, when humans for the first time in history set a step outside of our normal boundaries. We set a step on an asteroid awaiting their return. We went on moon, or went to moon. And I want to quote at the back of the thesis Carl Sagan, who says, "Exploration is in our nature. We began as wanderers, and we are wanderers still. We have lingered long enough on the shores of the cosmic ocean. We are ready at last to set sails for the stars." And with this idea, I also started or continued into my PhD. I wanted to contribute to this very fascinating way of how we can explore further, how can we go deeper into space, how can we expand humanity to an interplanetary species and not just be confined to the limited space of Earth. And if we do so, we don't just want to go there to be there. We want to go there to stay there. Not like the Apollo missions. We will, in this case, not just visit, but inhabit. So, very tough research question. How can we do it? ESA is having this concept, for example, where they have designed a rover who will be transported to the lunar surface. There will be a module for the astronauts, and the rover will break up the very soil of the moon, deposit it layer by layer over this habitat, and sinter it. So use microwaves to basically build a shield. Because the moon is a lot, but it's not a very friendly environment. Because you have high radiation, you have micrometeorite impacts, you have a lot of things which kill humans, and we want to avoid that. But besides infrastructure, we need many more things. We need power, so we need a way of supplying power to this new habitat. We need supplies, so we need food, we need medication, and so on. And we need transport to go there, to come back, or also to transport ourselves on the planet we go to, like Mars. So, I'm a biologist after all, and in the time where I was at NASA Ames, I saw this poster hanging in our office, and I was really intrigued by this grandiose view of how synthetic biology, I don't even want to say synthetic biology, but how just biology in general can contribute to making this dream of becoming an interplanetary species reality. And here you can see all the types of different ways how biology can contribute to a sustainable colony or a sustainable outpost. So you have food production via algae or via plants. You have biomonitoring, you have wastewater treatment. So for example, Lynn Rothschild, who is also here today, her group is working on how can we use sponges to filter water, so 3D printing sponges to filter water for the astronauts. Or also biomaterials. So lots of you remember Dominic Schmieden's work, who made nacre, biological nacre, for material production. So also these kind of things can contribute to a new Martian colony or moon colony. And today I want to talk about one particular one because that's the one my research was mainly conducted in, and that's biomining. Biomining means only you take biology as a way to extract resources from Moon or Mars. This can be all kind of resources, but for me, it was mainly iron and silicon. There's a slide missing. Okay. Anyhow, it was mainly iron and silicon. And we looked into 4 different organisms how we can do that. That's actually work done together with Rick Folger, who is also here today, a brilliant student of mine, who looked into the theoretical models of how we can use different organisms to extract iron directly from the Martian soil, or the lunar soil as well. And we only find one which is feasible, and that's the Shivanella onadensis. And throughout my defense today, you will hear this name quite often, because it was actually my little friend for the last 4 years. I worked mainly on this organism during this time. So Shivanella onadensis has the capability to take iron in one chemical form, iron 3+. We don't go into detail what it means, this chemical form now, but take iron from one chemical form into another, iron 2+, and these two together can form magnetite, which is this very specific ore, very specific mineral. This magnetite, in the end, can be extracted then, as the name already says, with a magnet. So therefore the name magnetite. And that was basically our workflow. So we used this bacterium, we put some lunar, Martian, or mainly Martian regolith, because it doesn't work with lunar regolith. Regolith is just a fancy word for soil, sorry for that. You will also hear this word quite often today. So whenever regolith is soil, but fancy without organic matter in there. So we take that, we mix it with the bacteria is changing the chemical composition, which leads to the precipitation of magnetite, and this magnetite can then be simply extracted via magnet. So also 2 students, Tom Arts and Sophie Kesterlein, who are also here, worked on that together with me. And just to give you a bit of an idea how we tested that, here you can see actually our Mars regolith simulant. So we were using basically a mineral composition, an ore composition, which was fairly similar to what we know that the Mars should be composed of. And in this picture, so this is the simulant, and in this picture on your left side, you actually see how on the top bacteria are growing in a liquid layer around this regolith. The bacteria are growing over 16 hours. In the bottom, it stays the same. And I put this picture because it also shows the interdisciplinarity of this research. Because this regolith simulant I got from my collaborator at Heriot-Watt University, Edinburgh. These pictures were taken at NASA Ames Research Center from a camera which was developed to the lunar exploration called Research Prospector. And I did the data analysis here in Delft. So, and this is actually the story of space exploration. It's a very multidisciplinary field, and I wanted just to highlight that here. No worries, I won't show too much data, because it can be a bit confusing, but I want to show you a bit of what the results were on the experimental side. So what you can see here is we put 10 grams per liter of this regolith simulant we used into a solution of bacteria, or into a solution without bacteria, which is the control here. The control in orange, the bacterial sample in red. And you can see after 72 hours of treatment with bacteria that there is a significant increase of material extracted. So we extracted this material with magnetic force, as I explained before, and if we treat it with bacteria for 72 hours, we see a significant increase in the material we can extract. And the same is true also after 168 hours, which shows that we can increase the quantity of material extracted via our bacteria, via our microbiological methodology. And we cannot just increase the quantity, but we also saw that we can increase the quality. So here you see different regolith simulants. So this one you already know, it's the Mars one, but there are also others. These are more moon-like, but we also tried to use them. And you can see the increase on the total or the central iron concentration in our sample. So that means when we extract this material from the regolith, we also increase by extracting it, the iron concentration. That's what we in the end wanted to do, because we want to have more iron, so we can build stuff with it, right? So we can increase the quantity of the material, we can increase the quality of the material. But what should we do with it? And that's where many of my collaborators came into game, because we wanted to try different approaches, how we can manufacture then this extracted material in different ways. So we used, or we thought of 3 technologies, we used 2 of them. We thought about plasma printing, which is applying a plasma stream on the regolith particles. We thought about LCM, which is lithography-based ceramic manufacturing, which is a process to 3D print ceramics, actually. And laser sintering, where you apply a high energetic laser onto these regolith particles to solidify them. And we were successfully doing 2 of them. One of them was done, like the plasma printing I did with Lynn Rothschild and her lab at NASA Ames and at Space Foundry, which is a spin-off company from NASA. And we were able to solidify the top layers of our regolith simulant. We, however, could not go really deep into the regolith because the plasma printing was not tuned for our particular process, right? So we could not really solidify the entire regolith. Very differently, a very different approach is the lithography-based process, where you use a binding material to bind this material together and really make forms out of it. And that's actually the forms we made out of it. We made these small cylinders, and we made these small cylinders so that we can test the mechanical properties. And we did it 2 ways. We tested the mechanical properties of bacterially treated material and non-bacterially treated material. But sadly, there's a cliffhanger. I don't have the results yet. So we don't know if we can really improve the mechanical properties already. But what we already know is that we can do great stuff with this technology, because this was demonstrated by Isa and Leachers together. These are nuts, bolts, screws, drills produced by lunar regolith simulants. Just adding the binding material and the 3D printing approach. And if we can see that we can increase the material, improve the material properties, and make them these different shapes, that would be a huge game changer in developing technology for a sustainable space colonization, where we actually go to the planet, where we go to Mars, where we go to the Moon, and use the resources, the very resources we find there, utilize them, and build up our habitats. And that's actually what my main part of my research was on. We also designed some mission architectures. I don't want to go into detail here, but we also thought along with some NASA and ESA scientists, how can we make that really happen? So what is the way of, what kind of rockets do we need? How expensive is a mission like that? Don't ask, it's really expensive. What kind of infrastructure do we need? All these kind of things. How can we test it beforehand? How can we certificate it? Make it space-proof? Adapt it to the radiation fields of the hostile space environment? Adapt it to partial gravity and so on. And we also did that in models. And also here, Rick Volger and another student of mine, Marijn Timmer, who is also here, worked really hard to get these models, this fluid dynamics right, and to build this bioreactor in which we could perform these processes. But time is running, and there are some other topics in my PhD I want to just shortly throw at you. I mean, I guess you're already pretty loaded with the dense information of this part, but right in the beginning, I said to new frontiers, microbiology for nanotechnology and space exploration. So let's come a little bit to the nanotechnology part. Just another 5 minutes, because that's the time I have. So we actually started with bioprinting, where we used an additive manufacturing process to 3D print bacteria. So this bacteria can produce materials in our scaffold. So we build up a scaffold, a 3D printed scaffold, and bacteria in there are producing material of interest. In this case, it was just a demonstration with a red protein. So the bacteria who had this red protein, so this is a 3D printed cube, and the bacteria who had this protein actually became red. It doesn't look that fancy. It was a hell lot of work, and I was really happy when I saw this red color. And besides that, we also looked into a complete different world of directly using bacteria for the production of nanomaterials, mainly graphene. So we were working on graphene, which is this extremely popular, extremely hyped nanomaterial because it's multiple times as strong as steel. It's much more conductive than silver. It's just amazing. It's just one atom layer thin. So it's just like single layer graphene is one atom layer thin and has these amazing properties. And we wanted to do we wanted to develop a way how we can make the production of that more sustainable using bacteria. And we just published this work also this year. It kind of works. And that's like the main story of biology. In any case, it kind of works always. But it takes a while to come there. And here you can see the comparison of chemical reduced graphene. So these are really single flakes of graphene. You have to imagine they are 1,000 or 100,000 actually of a millimeter, these flakes. And we measured single flakes of them in their conductance, so how much electricity they conduct. And you see in blue chemical reduced ones, so the more standard way of doing it, and biological reduced ones. And you see that the chemical one are a bit better, but in the end, there's it's very similar. So how steep the line goes shows how conductive the material is. But I don't want to spend more time on that. And instead, just summarize shortly. I also have a little break between before I get questions from the committee. So the first, or the big topic of my thesis, which spans over 5 chapters of it, can we extract iron from Mars? And if so, how could we do it? And we showed that we can increase the quantity and quality of iron with our bacterial methodology, and therefore we can extract iron from Mars with bacteria, which is great. Then the second topic was how to design a space mission. I didn't really go deep into that, but this is just how we make the first thing happen, right? I mean, we have to design a space mission to really make use of what we developed as a proof of principle in an experimental sense. The third thing is bacterial 3D printing possible, and there has been work done before us already, but our main thing was to make it as cheap as possible, as reliable as possible, and available for everybody, actually. And also this worked. And can be used to produce microbes to produce graphene, and kinda. It's not as good as other methods, but it works. And then there are 10 topics I don't talk about because they all didn't work. And that's the story of a PhD. Thank you. And of course, if you have any burning questions right now, please feel free to ask them in the next 2 minutes. Go ahead. Okay, I just confused everybody. Very good. You will be more confused afterwards even.
I think we can better make the photos with you with the power and info later.
Yeah.
Because now there is less time.
Yeah.
Kom even kijken of alles goed gaat.
Yeah. Just finished. So, yeah, as the committee is seeing it as well.